So we are going to talk about growth and decay today. You may have been exposed to this topic in other classes. I'm thinking off the top of my head, AP Cal, or sorry, this is Cal. What's another one? AP Chem. Yeah, anybody in AP Chem? Have you done growth and decay?
No.
Really?
Yeah.
Okay. You did it last year in pre-calc.
Yeah.
So you've seen it using the infamous Pert equation, which we'll talk about. But we're going to take a calculus approach to it today. So, let me get my clicker to work. Come on. Sometimes it needs to be. There we go.
Need some encouragement.
Even though I took the topic out of the title of the topic out of the textbook, we're not going to do population over and over and over again. We have a whole bunch of things today. We're going to look at radioactivity. We're going to look at Newton's law of cooling. We're going to talk about some bacteria, all kinds of fun things. Okay, so we're going to use the Pert equation. The difference between last year and this year is this year we're going to explain where that thing comes from. Last year you were just given this magical formula and you were asked to solve things using it. In calculus, we can actually generate where that comes from. That's what I just said. And then, of course, you should be able to believe in yourself, because I believe in you.
That's awesome.
You are strong enough to make it through. I believe.
All right.
Hope that helps a little bit on Friday. Okay. Good. Here we go. Pretty question. So, you've seen this before. Now, you may have seen it in different forms, and in fact, when we get into some of the problems, the form might change. By the form, I mean some of the letters will change. Okay? So, what does the A stand for?
Final
Oh, you have it on the slideshow. Never mind. Thank you. Never mind. Final amount. I should have excluded that. I'm an idiot. Sorry. So I'll just click. Okay, there we go. T is time. R is the growth or decay rate. Sorry. Let's see if you remember from last year. Tell me about the different values of R and how they affect the problem. What do you know about R? Other than the fact that it's a pirate's second favorite letter.
It's C.
The C.
Oh, that's funny.
What can you tell me about R, the rate?
It's a rate.
Good. It's a good start. It's what? No, not that rate.
Okay.
That's a growth rate and a decay rate.
Okay.
Anything else? Go. Good. For those of you that didn't hear that, if it's positive, it's a growth. You would see something like that in the spread of disease, some investments. Hopefully you get a good investment, you would have a positive growth. Decay, if it's negative, it's a decay like radiation, that kind of stuff. Okay? P naught, as that's commonly referred to, is your starting amount, A is your final amount. Now, those letters will change. For instance, yes?
Why is there a D in there? We have to get that.
Yes. Yes. It's not an O, it's a naught. It refers to the starting amount. You know, like in physics, you would do velocity, but then you'd have V naught. That's the starting amount. Oh, okay, you could do that too. Hence the reason I said these will change. Any other questions? And down at the bottom there, that y equals c e to the kt is the most common form that we see with calculus. You'll see why why the p becomes a c as we work through some of these problems.
Is it because it's constant?
Bingo. It's an integral constant. Any other questions? Excellent. Here we go. We're going to start with some bacteria. So, one of the things that we deal with is this idea of being directly proportional. Have you ever heard the term proportionality constant, other than me just saying it now?
Yes.
What is it?
It's the slope of a line that goes through 0, 0.
Not necessarily. A proportionality constant is a constant that, this is ridiculous. Proportionality constant is a constant that relates the proportionality of two different things. Okay. What does that mean? Okay, it means this. If we have a function that relies on the bacteria, assume that the rate of increase is directly proportional to the number of bacteria present. So let's define some variables here.
So we increases in the same, like it increases the same amount over the same interval.
Correct. I'm going to define B as being the number of bacteria present, bacteria, and T is already defined as time, so I think we're good to go. All right, so if I look at this sentence, the rate of increase of bacteria, that would be dB dt. Okay, because remember, as Giselle said earlier, rates are also derivatives, okay, is proportional to the number of bacteria present. So we introduced this proportionality constant, which we usually use a K to represent. Which is why also on the previous slide, there was a K in the slide, because that's going to work itself into this. Okay? Now, if you recall, I'm almost sure that last year in pre-calculus, you did at least one bacteria problem or a disease problem. Am I right? You don't remember, do you? You do remember. Okay? And when you did that, you were just given the PERT equation and you plugged and chugged and solved for some things. We're going to take a calculus approach to this. You know what this is. Okay? This is a separable differential equation. We want to get back to an equation that we can work with to plug and chug into. So I'm going to do exactly what we worked on yesterday and get to this. Because again, as I tried to drive home yesterday, the most important thing is separating the differentials. All right, what's next? Integral. Tori, what's the integral of 1 over b d? Oh, hold on. Let me ask you a question first, Tori. In the left side of my equation, what's the variable? Say again? B as in badger. Correct. Outstanding. So what's the antiderivative of 1 over b? Beautiful.
Don't forget the absolute value.
Ooh, I'll come. Is that you?
Yeah.
Excellent. I'll come back to you in a second. Thanks for the help. You almost think I planted that. Tori, back to you. On the right side of my equation, the integral of k dt, what's the variable?
T.
Outstanding. So therefore, what's the antiderivative of k dt? KT.
Let's see.
Okay, now, oh, thank you. I was going to get there. Yesterday we talked about always sticking the plus c with the x's. We don't have x's and y's. We have b's and t's. Chris, back to you. You said a very astute observation earlier. What was it?
Are you need absolute values around the B?
Outstanding. From a mathematical standpoint, I should have absolute value bars around the b. Why did I not put absolute values around the b? Is it A, because I screwed up and realized I made a mistake, so right now I'm trying to BS my way through the mistake and now and blame Chris for this? Or B, is there a legitimate reason, Maria?
You can't have a negative number of bacteria.
Yeah, you can't have a negative number of bacteria, so we can assume that we don't need the absolute value. But again, kudos to you, Chris, for keeping me honest. Okay, what next?
Solve for T.
No,
Solve for C.
no. Well, yes, how?
Plug and chug.
Not yet.
Oh.
What else can we solve for?
Deal with the numbers up top.
Could be K, but it's not.
B.
We're going to solve for B. Okay. E2 trick. What's the left-hand side become? B. First time through, I'm going to go slow and remind you about what I talked about on Wednesday, and that is, remember when I asked you Wednesday about this?
Yes.
Okay. By the way, in case you forgot, it's x to the fifth because you add the exponents. So if I go backwards, this is the same thing as e to the c times e to the kt. Is everybody okay with that move? Okay, we're good? Excellent. All right, what's e to the c? Just plain old C. That's where the PERT equation comes from. Now let's review. In this particular problem, what does B stand for, Bryce? And it's not Bryce.
Stands for. Oh, bacteria present.
Yeah, it's a number of bacteria. What does C stand for?
Constant.
Which in this case stands for?
Initial amount of bacteria.
How many we started with? K is the growth rate, T is time. Okay. That's the first part of the problem. That takes care of part A. We have a general form. Oh wait, no, we're not done with part A because I don't know what my starting amount is. I can figure out my starting amount by doing a little bit of work. So if I go back to my problem, the number of bacteria in the culture increases from 600 to 1800 in 2 hours. What's C? 600. Okay, so this one we get lucky. It tells us what the starting amount is. This is close to being the general form, but when you have the general form, you're only going to end up with 2 variables, the number of bacteria and time. I need to figure out what the growth rate or decay rate. Which one is this? It's a growth rate. We're all in agreement. So now the reason I asked that, it seems like an obvious question, but as you're solving for K, if you solve for K and you get a negative number, you screwed up because we know it's got to be a growth rate. How do I solve for K? I hear talking.
You can plug into the, you were given all the information, there's nothing you don't know, so you just plug it in.
Okay, good. Let me back up for a second. When did this happen? What was T? 0. Okay, so if I go back to this and I plug if I plug 0 in for T, what's e to the 0? 1. I have 600 bacteria, that's why C is equal to 0. Okay, so even if you get kicked in the head by a donkey and you forget that C represents a starting amount, you can still solve it using the fact that at T equals 0, I had 600 bacteria. As Maria said, we then have this second chunk of information. There are 1,800 of them 2 hours later. Therefore, in this equation, what's B? I'm going to change colors, by the way. 1,800, and what's T? 1,800 is equal to 600 times e to the 2k. Bust out your calculators. Huh?
You gotta keep it as natural log.
What is natural log?
I divided by 600 and then put the rest of log both sides.
Well, that's what I'm going to do. I'm not done.
Keep it as natural log or?
No, you should probably, well, I'll get there. Hopefully you didn't need your calculator to do 1,800 divided by 600. Liz?
Do you have a calculator?
I do not, I'm sorry. You could share.
Yeah,
Okay,
thank you.
no problem. How do I solve for K? Natural log of both sides. Natural log of tree is equal to the natural log of e to the 2k. Natural log of 3 is equal to 2k. K is equal to the natural log of 3 divided by 2. Okay. Get it? Okay. See what I did there? Jacqueline, you're with me, right? Saw you smile. Thanks. Appreciate it. Glad you're here. I believe in you, Jacqueline. Yeah. May, did you smile also?
Oh, after you pointed out the Jacqueline smile, I did.
I'm sorry, what was that?
After you pointed out the Jacqueline smile, I did.
Okay, but you didn't smile initially.
No, I'm sorry.
Okay, I'm not sure how much I believe in you anymore.
She didn't smile at not.
Okay. What's that?
She didn't smile at not.
Oh. That's good. That's good. Okay, if you type that into your calculator, please do so. You get a number. What is that number?
Wait, 5, 4,
K is approximately equal to
.549.
0.549. Okay, so as I've mentioned a billion times, the College Board expects everything rounded to 3 decimal places. However, in a calculation like this, you're expected to store that number, not use 0.549, because it matters. You'll see in some of the other examples we have, we're going to have things with like 5 zeros in front of it, so you want to store numbers. But when we're doing the problem, you can either leave it as a natural log of 3/2, but we all understand that's a pain in the butt to write. You can write it out in your problem as 0.549. So for instance, to answer part A, I would write B is equal to 600 e to the 0.549t. Dan, you had a question?
That was my question.
Okay. Once I...
Why, well, maybe I'm pointing your head here, but why wouldn't you just leave it as ln3/2? Because you're multiplying it by 4 at the end of that.
But you don't
and
always
can
know
just
that you're gonna multiply
cancel-
by 4.
Well, yeah.
Yeah, but in this case you could,
Obviously.
sure.
Okay.
Now, once we get down to this, there are only 2 possible questions to ask. Question number 1 is, anybody? Oh, this is awkward. Liz?
What's the time at a certain number of bacteria?
Bingo. Here's a certain number of bacteria. How long did it take to get those? And the other question?
Here's a certain amount of time on bacteria.
Bingo. That's it. There's no other possibility there. Do we need to go through the calculation for part B, or can you all plug 4 in there for T? We're good? Okay. Eddie? Yeah.
Sorry.
Don't be sorry.
I just did B, right, and the answers, it's like 53, or 5,399.99999 repeating. How would you round that for the college board?
If you get to something like 0.999999, odds are it's probably a small calculator error and you could just bump it up.
Okay.
If you get an answer like 1535.567, that's weird because we're talking about whole bacterium. One is plural and one is singular. I don't really care. That's why I go into math. But
Bacteria is
the way that problem is solved is 99% of the time on the problem it will say to the nearest bacteria, to the nearest penguin, to the nearest school-age child. They're not expecting you to, and if that statement isn't included, then you give the decimal approximation and don't round.
Okay.
Okay? In other words, round if they tell you to. If they don't, stay with the 3 decimal places.
So the number of bacteria, we just put like B equals 5400, which is the answer, or like B equals 5400 bacteria, or 5400 bacteria.
A good rule of thumb is anytime you have a word problem, always include units if you can.
Can we still put like B equals and then circle that?
B equals 1500, whatever. What did you get for an answer, Liz? 1500,
Or 5,400.
5,400 bacteria. Okay, any questions on the process here? Notice when I started this problem, I had to come up with this equation on my own. However, I will tell you that that form of the question repeats itself a lot in the problems. On the homework tonight, I'm going to ask you to do this on the first 2 problems, and then that's it. From that point on, we can just dive right into the PERT equation in whatever form you want to write it in. Okay. We good? Questions? All right, what are we doing next? Radiation? Is that it? Yeah. Yeah. Radium. Okay. So, there's 2 ends of this discussion we need to have before we move on. Are you all familiar with how radiation works?
I do not understand the concept of half-life.
Okay, beautiful. So there's one discussion we're going to have is what's called a half-life. The other half we're going to have is what's called a doubling time. So let's do the half-life first. The way half-life works, or what that means, is that that's the amount of time that it takes for half of the material to just disappear. Okay.
Why do we care?
So I take a ton of radium and I leave it in a field. 1,600 years later, when I come back, there's going to be a half a ton of radium sitting there. Does that seem simple? Then, after another 1,600 years, I'm looking at a quarter ton. Because the half-life is so long, you see, will all the radium ever disappear? Why, Max?
Because it just keeps getting smaller and smaller.
Yeah. Good. But never gets to zero.
Yeah.
Yeah, we keep cutting it in half and cutting it in half and cutting it in half. Okay? Because certain elements in radioactivity are so bad with half-lives, that's why things like Chernobyl, they can barely go. I think just now they can start going into Chernobyl in heavily protected suit. Do you all know what Chernobyl is?
Yeah.
Okay, just want to make sure. They're just now being able to go into Chernobyl, and that's radiation that has a half-life of well over 1,000 years. They're going in, I don't know, when did Chernobyl happen? No, I don't think that.
86.
Is it 86? Okay, 86. And that's what, 14 and 23 is 37 years ago? Did I do my math right? On a material that has a very high half-life. Okay, so that's one end, is half-life. Do you understand it now? Is everybody good with half-life? Okay, doubling time is something you commonly see in investments, and it's the amount of time for a material to double. So let's suppose you graduate from high school in May, and your grandma Marge gives you $1,000, and you put it into a bank account, and it sits there gathering interest. One of the questions you might ask yourself is, how long will it take for me to double my money? Okay, doubling time. It's the opposite of half-life. Okay, we good? We're going to probably do more problems involving half-life than we will doubling time. So here's what we know. Radium has a half-life of 1,600 years. I'm not even going to look at A and B. We're going to play with this a little bit. So when you're solving half-life problems, you have two approaches to it. I can apply a numerical value to the amount of material that I'm starting with, or I can just use a variable. Okay, so I'm going to use R, capital R, to represent the amount of radium. So I have that to start. I'm starting with R, whatever, ounces, we're milligrams here. R milligrams of radium, and my time is 1,600 years. So how much will I have left after 1,600 years? 1/2 R. Now that seems to be a problem because I have two variables in the equation. But my first step is going to be to divide by R to get E by itself. So 1/2 R divided by R is just 1/2. Okay? If that doesn't make any sense to you, that's okay. Just assign a number to R. I've got 100 pounds of radium. After 1,600 years, I'll have 50 pounds, and I'm still going to get that 1/2 thing. Questions? Good. Solve for K, please. By the way, will K be positive or negative? Negative. Okay, go ahead. Solve and store that number.
Mr. Reedy,
Yo.
we actually did do this.
You did.
Yeah, I'm getting flashbacks now.
Do you need to go see your counselor? Or
No.
those like bad flashbacks? Like,
I mean, a little.
okay,
Yeah.
I get it.
Half-Life wasn't really my thing.
I understand. You're going to be okay?
I think so.
Okay, good, good.
Yeah, the power of 10 times.
Why do you want to know that? Why do you want to know that?
to calculate. So we know, for instance, what a lethal amount of radium is to a human being. So you want to be able to calculate how long is it going to take to get to an acceptable level.
As bigger quantities of
It's all the same. It's half-life for everything.
How does 100 pounds of radium
It is.
50 pounds of 1 pound of radium ends up half pound the same amount?
It's a percentage, it's not a quantity. So it doesn't matter how much you have, it still all just goes away. I'm not a chemist. I don't understand it, but I know it happens. Yeah, it just, I don't know if the word disintegrate isn't the right word, but it just, and evaporate isn't the right word, it just disappears. I don't know how.
Decomposes.
Thank you, decomposes. Max, what's K?
I got negative 4.332 times 10 to the negative.
Okay, so let me write that down. 4.332 times 10 to the negative fourth. We probably don't want to do calculations with scientific notation, so let's convert that. Everybody know how to convert this? We're going to move the decimal place to the left 4 times. 1, 2, 3, 4. Fill in all the loops. Negative 0.00043332. Hi kids, how we doing? Have fun at lunch. Okay? So you see now why you want to store that. Which means if we do any radium problem, we can at least now we know the rate. And notice I did that without even looking at what the problems are asking us. So part A says, find the formula for the amount of Y remaining from 50 milligrams, the amount Y remaining from 50 milligrams of pure radium after T years. So I probably should have read the problem because the problem's telling me to use Y instead of R. Okay. What's my starting amount? 50 milligrams. So we get Y is equal to 50 times E to the negative 0.000433 T.
Wait, is the problem that you use Y, isn't that with the, because aren't you using R for C, so it's fine? Weren't you using R for as the C value?
It doesn't matter. I guess you're right. Getting back to your discussion though, talking about radiation in this respect is very long-term half-life. There is also radioactive things that have a very short half-life. So you would want to know, like, there are certain procedures that involve radiation, and you want to know how long that radiation stays in the system. You know, you're giving somebody an X-ray, they're going to be exposed to radiation. How long does that stay in the body? You're giving somebody swallowing barium to have a procedure done. You want to know how long that's dangerous. So half-lives aren't always these grandiose 1,600 years. Sometimes the half-life is 45 seconds, depending on the material. Okay. Giselle, you remember that, right?
Yep.
All right, good job. Thank you. Okay. Any problems?
Why would the rate be like constant if it changes? If it's like, or like if the half-life is 1,600?
I don't know if I understand your question.
I don't know if I understand it either.
Okay.
Like, wouldn't the rate change based on
The half-life?
Yeah, because it's
Yes.
like exponentially decreasing, right?
If we went and found a different material, if we found something instead of radium, let's say we did plutonium. Somebody look up the half-life of plutonium, please, real quick.
But like you said, like after that half-life, it's like the next, it's like half of that.
But it's always going on, right? So, I mean,
So that'd be the same.
I'm not trying to be funny. It's
Yeah.
not like this pile of radium sits there and then after 1,600 years,
Yeah.
50, it's always decreasing, but it's decreasing, and at that 1,600, then half of it is gone. Anybody?
20,000.
Say again?
How do you round something just like 3 zeros after the decimal point?
You would, if I was rounding this according to the AP, I'd go 0.000433. You got it?
That's 20,000 years.
So the half-life of plutonium is 20,000 years. Now again, different materials have different, and I can't think of an element that has a half-life of something like 10 minutes, but they're out there. Okay? Do we need to talk about part B, or are we good? Where would you plug the 20 in?
Why?
For Y, correct, because we know the starting amount now. It's not time, it's the final amount.
We keep this as a decimal unless the count is surrounded.
Correct.
If it's, so this one I think ends in 9, it's like 9 and then it would round up, so we do 0.085 or 0.0850.
Good question. I think I've talked about this in the past, but I'll do it again. If you have an answer like this, okay, and you have to round to 3 decimal places, the AP accepts rounding, following standard rounding mathematical rules, or they also accept truncating.
If the 5 was a 9,
Yes.
So rounding up would,
Okay, so let's suppose you're saying if this is a 9,
yeah, so you round up that becomes a 0.
then I would answer 123.440.
Okay, is that last 0, we should include that?
You won't be penalized if it's not there, but it's a good idea to always show 3 decimal places. You understand the difference between rounding and truncating, yes? Truncating, you just chop off all the numbers and go with it. Otherwise, you round using math rules. So if, going back to this being a 5, the AP would accept 123.435 or 123.436. And you'll see when you start looking at grading rubrics, they'll give you both answers, and that's why you get 2 answers there. Good? Problems? You will see some problems on the homework tonight where you have to get a little creative. For instance, they might not give you the starting amount. You may have to solve for the starting amount using the information that they give you. Okay? You got to get a little creative sometimes with these types of problems. All right, we're good? I think we're doing law of cooling now, yes?
Wait, how would you do part B? Would you just plug in 20 for R?
20 for Y. Final amount.
Oh,
I changed to an hour. Yeah, yes.
okay.
Yeah. And then, of course, remember when you're doing this, you divide by 50 first before you take the log of both sides, or natural log of both sides. Okay, let's talk about Newton's law of cooling. This one's a little bit different, only because it requires a little bit extra work. Right? According to Newton's law of cooling, the rate at which an object cools is directly proportional to the difference in temperature between the object and the surrounding medium. Okay, let's go back to red, and I'm going to stop this right here. Okay. The rate at which an object cools, all right, so let's call that dy dt, is directly proportional to the difference between the temperature of the object and the surrounding medium. The temperature of the room, the temperature of the water bath that you put it in. So this one, where is it? Here it is, 75 degrees. Whoops. Okay, so our starting formula looks a little bit different there. Just to keep things all legit, y is equal to the temp of the object. So notice in this problem, I don't tell you what the starting, well, I guess I do tell you what the starting point is, don't I? An object cools from 125 degrees to 100 degrees Fahrenheit in a half hour. When surrounded by air temp of 75 degrees, find the temp at the end of the half hour. So I'm going to go through the whole process we did before to get this into an equation that we can use. So dy is equal to, this will be 1 over y minus 75 equals k dt. We've done this already, so I'm going to go through it quickly. Take the integral of both sides. The natural log of the absolute value of, no, I don't need the absolute value again, of y minus 75 is equal to kt. E to the, oh, plus c. So that gets me y minus 75 is equal to c times e to the kt. I did this Wednesday, but I'm going to do it again. Notice this, I made a big jump here. I was hoping you were all with me, but you should realize that that actually requires a UDU. I just left it out because I recognize that following a pattern. Because it's a linear equation, the UDU is going to come out in the wash. Yes? Or do you need clarification there? We're good? Excellent. All right, what do I know? Liz? Good, time is 30 minutes. Are we going to use 30 minutes or are we going to use 0.5? Is there any indication in the problem that you should use one or the other?
It says half hour.
It does say half hour, so we're going to go with 0.5. You could do 30 minutes as long as your answer's all, as long as all your work's in 30 minutes. Okay, so I know that t is equal to 0.5. Okay, what else do I know? Sure. T equals 125? C. Why? Yeah. What else do we know?
Why?
What would y be?
The initial temperature that I have to say.
All right. So let's go through this and play with this a little bit more. At t equals 0.5, at a half hour, what's the temperature? Come on. What's the temperature after a half hour? 100. So y is equal to 100. Okay. Instead of this being a C, Gesundheit, let's make that a y. So the temperature is 125 when? T equals?
0.5.
No.
Or 0.
0. Good. So I'm going to go through the derivation that I skipped in the first problem and show you how we get C being 125, according to what Sarah told us. So what does that mean? That means 125 minus 75 is equal to C times E to the K times 0. So what's C? 50. I agree with you wholeheartedly that it would appear in the beginning of the problem that C is equal to 125. But the reason it's C and not Y naught is because C in this case represents our starting constant. It doesn't necessarily represent the starting temperature. Okay, which is why I went through this derivation. When do you have to do that? Pretty much only when you see a law of cooling problem. Anything that's set up as your standard rate equals proportional times a constant or times a variable is going to solve with C being the initial amount. Okay. So that gets us to this. Y minus 75 is equal to 50 times e to the kt. I've eliminated one of the variables and turned one of those variables into a known quantity. The other thing we need to find is k. So then I would use this information to to solve for k by doing 100 minus 75 is equal to 50 times e to the 1/2 k. And I think you see where this is going then. So we're getting a little repetitive here. You solve that for k, store that number, that now becomes your rate. And knowing that, you then have your general equation for this law of cooling problem. The only variables you have then are T and Y. And that's the goal. When it says come up with the general equation, that is going to reduce it to only those two variables. So again, we only have the two questions that Liz answered before. After how much time, what's the temperature? That's question number one. Question number two, here's the temperature. How long did it take to get to that time? So I wanted to show you a law of cooling because those pop up every once in a while, and it doesn't match like the other previous two problems we've done. Preguntas? No? We're good? Okay. So again, on the homework tonight, I want you to go through this derivation process, that we did here for only the first two problems. The other ones you can dive right into the PERT equation. Okay? Spread of disease, zombies, exponential growth. Yeah, you do that calculation. We're good? Yeah, okay, good.